the topic I wanted to discuss in this assignment is to determine the function h of theta for small angles. We came across this function when we tried to apply dimensional analysis to this period of a simple pendulum. We got as far as tau equals the square root of h theta times the square root of g over l, or l over g, sorry. And yeah, but this h of theta remained a bit of a mystery, so I was kind of curious what this looked like. I devised an experiment which basically involved building a pendulum out of some mechano, a protractor, and a long length of string, and yeah, setting it in motion. I recorded the time for 20 oscillations of each angle. So these are my results, dividing by 20 to get the period, and then to get h of theta, I rearranged this kind of equation. So yeah, it's g tau squared over L. My G I took to be 9.81 and my L was 1.42 meters. When I plotted these results, I got a straight line. This is perhaps a slightly surprising result because it basically means that h is independent of theta. And if h is independent of theta, that means that tau is independent of theta. Basically, if you start with a tiny angle or a huge angle, well, as long as it's small, the result will be the same. The period will be the same. Again, this is a slightly surprising result because you might think if you start further away, it'd take longer, but it doesn't. Perhaps it shouldn't have been such a surprising result to me because I knew from classical mechanics that it should be 4 pi squared, which is 39.47. But yeah, this kind of my result here, 39.5, backs up this 39.47 from classical mechanics, and is also an interesting result to me anyway. Yeah, I think that's all.